Yeah, so the recording has started. Okay, so welcome everyone. Today we have Arun from IIT Kanpur, who is in his final year of his PhD. Uh, Today he will be talking about persistent memory and especially stack persistence. This work appeared in HPCA 24 just last month. So over to Arun.
Yeah, thank you, Vishwa. Hi everyone. I welcome you to today's talk on program stack persistence in hybrid memory system with DRAM and NVM. So consider a scenario: we are running an application and a crash happens, such as power failure. So ideally, what we want is that once the system comes back, so we want the application to start executing from the exact point where it was before the crash. So to have this kind of facility, what we need is that we need to save and restore the state of the process. So traditionally, what we used to use is that we used to use disk secondary storage for saving state of the process, but it has file system and storage overhead. Given that now we have hybrid memory system with NVM, we can use NVM for saving the state of the process. But NVM also has problems like it has a high read-write latency and limited write endurance. For saving state of the process or maintaining the state of the process in a hybrid memory system, we can have different approaches. So in one approach, we can maintain the state completely in NVM. Then we have to make sure like all the state updates reaches the NVM. Another configuration is that we can maintain the state in DRAM and we keep saving or resisting the state to NVM. On the third configuration, we can have a hybrid mechanism where some part of the state is in DRAM and some part is in the NVM. And whatever state we maintain in DRAM has to be saved to NVM to ensure the persistence of that state. So if we talk about state of the process and for achieving process persistence, the memory contributes majorly to the state which needs to be saved. So since memory contributes majorly, the efficiency of memory persistent technique is important to have an overall good performance of process persistence. So at this point, we want to make a claim that for stack, maintaining stack in DRAM is an efficient method in a hybrid memory system. So through this talk, we will show it is the case. So now we will see two category of techniques for ensuring memory persistence. So the first category of technique is called in tandem technique, where the technique works in tandem with the program execution. So one example to such technique is logging. So where, as the figure shows, a log entry is created for any write happening to the memory area. Uh, Timestone, SSP, Romulus, these are some examples of techniques which works in tandem with the program execution. And we will be comparing our work Prosper against these works. Another category of technique is called periodic checkpoint. In this category, in an interval, we keep observing or noting down what all memory modifications are happening, and only at the end of the interval we make a decision to decide what to copy. So here in this scheme, writes or modification happening to overlapping or memory areas will be coalesced and persisted only once. So coming to stack, even though the size of the stack is small, but that number of memory operation to stack is significant for some applications. So one such example is shown in this diagram, which is a gap sphere, where we observe that 70% of memory operations starts to the stack. So now let's see whether how can we use in tandem technique for ensuring stack persistence. But the thing is that in tandem techniques does not work good for stack because of this usage pattern of stack, which is grow and shrink pattern of stack. So to demonstrate that, take this example as a snippet of this program. So at line number 9, we are making a function call, and before the function call returns, the diagram shows the stack frame of that particular program. And once a function call returns, only the green part which is highlighted in the diagram is an active stack region, which is relevant for stack persistence. But a technique, in tandem technique like logging, for example, will create log entries for the entire stack region, not only for the active region, but for the entire stack region, the log entries will be created. So now look at the periodic checkpointing mechanism. What are the benefits if we use it for stack persistence? Periodic checkpointing provides stack pointer awareness. So what I mean by that, what do I mean by that is that at end of the interval where we want to decide what to copy, we can always limit the operation that we need to do to the active stack region. So any memory persistent technique can be called stack pointer aware if we can limit the operation which needs to be done as part of the persistence scheme to the active stack region. And periodic checkpointing is one such scheme. And periodic checkpoint also allows keeping stack in DRAM and avoiding access writes to NV. As we have seen earlier, there are applications where there are lots of memory operations happening to stack, and keeping stack in DRAM is a wise option given that accesses are there. And periodic checkpointing also allows the stack pointer awareness. That is, when copying from DRAM to NVM to ensure the persistence, we can limit the copy operation only to the active stack region. And when it comes to stack, all the operations are inserted by either the compiler or runtime. So a periodic checkpointing with OS assistance gives visibility to the stack so that the copy operation can be done from DRAM to NVM. So overall, from these benefits, we have seen that a periodic checkpointing based scheme is good for stack persistence. But however, there is an issue or there is a scope for improvement. What is that is in traditional systems, the memory changes are tracked at page granularity. So in this figure, we can see that the gap between tracking memory changes at a page size and 8-byte granularity. The gap is highlighted for gaps PR benchmark. And for stack, if we think about stack, the small size changes are very common for stack usage, like a local variable change, things like that. So for stack, a sub-page page granularity data tracking is important to reduce the overall checkpoint size. Now we will look at how Prosper can help in periodic checkpointing. Prosper allows tracking changes at sub-page page granularity, then allows checkpointing at a sub-page granularity. So this diagram shows a very high-level view of Prosper, which contains a software component, a hardware component, and interaction between them through a set of parameters. And the software component is part of the operating system. The job of software component is to collect the required parameters. The parameters are what is the stack range which we need to be tracked, and what is the tracking granularity. So Prosper, we can configure it with a different tracking granularity like 8-byte to 16-byte, 32-byte. So what is the current tracking granularity which we are interested in, and what is the bitmap area size, area which need to be used. So bitmap area is nothing but where this Prosper will keep noting down the memory changes as a bit. So the base address of that bitmap area has to be passed as part of a parameter. And the job of the hardware component to track what all stack modifications are happening. And the hardware component keep noting down the stack changes as a bitmap in the DRAM memory. So at the end of the interval, the OS inspects the bitmap in DRAM and copy stack from DRAM to NVM for persisting it. So now we will see some questions that we asked ourselves when we are designing Prosper. So as Prosper inspects all stack stores happening to the stack, so how Prosper hardware should interact with loads and stores, demand loads and stores happening from the core. So the design of Prosper is that it should not store loads and stores request from the processor. Also, the Prosper hardware generates a bitmap store request for setting the bits, so that the bitmap store generated by Prosper should be minimal, such that the interference in the memory hierarchy with the loads and stores generated by the processor should be minimal. So for that purpose, we have a lookup table in our data tracker, which allows in coalescing the bitmap store request. So I request everyone to look into our paper to have a detailed design and how the working of lookup table, the specifications of the lookup table. And second question that we asked is when should the OS utilize the metadata? So as we saw earlier, the OS uses the bitmap in DRAM for copying stack changes from DRAM to NVM. So OS should ensure that all the bitmaps modifications generated by the processor hardware has reached the memory hierarchy before consuming it for the copy operation. So we used Gem5 full system simulation. So we used two setups. So in setup one, we used GemOS. GemOS is a minimal OS. So using this setup, we measured the end-to-end checkpointing performance. And in the setup two, we use Linux. This setup is used to measure what is the hardware overhead of dirty tracker hardware. And the table shows the Gem5 configuration that we use for our experiments. So this result is for if we are using a memory persistent scheme for stack persistence, how the performance is. So here we are comparing with SSP. SSP is a shadow page based scheme where two physical pages are associated with a one virtual page, and modifications are directed to these two physical pages. And SSP has a background thread which merges these two pages, these two physical pages. And we have varied the thread invocation frequency from 10 microseconds to 1 millisecond in our experience. And Romulus is a dual copy mechanism. So it maintains a main copy and a backup copy of data in NVM. And for this experience, we used Prosper with tracking granularity as 8 bytes. And that the figure shows on y-axis the execution time with one of these memory persistent scheme applied for stack normalized to execution time when no persistent scheme is applied. Prosper helped to reduce stack persistent overhead by on an average by 2.1 times when compared with state of the art SSP when thread interval is set to 10 microseconds. And compared with the conventional system's dirty bit scheme, Prosper provided maximum 1.2 times reduction in overhead for Graph 500 SSSP workload. And when we compare with dirty bit, the Prosper's benefit compared with the dirty bit comes from reduction in the checkpoint size. So as we can see for a scheme like stream, the stream benchmark is a micro benchmark where we modified all entire page. So there Prosper does not provide any benefit compared with the dirty bit because anyhow the entire page is modified, so everything has to be copied. So there is no reduction in checkpoint size. So Prosper does not provide any benefit there. So overall, Prosper performed better than Romulus and state-of-the-art memory persistency scheme SSSP. So in these results, we are looking at what is a performance when we want to persist the entire memory area, which consists of heap plus stack. So here we are looking at a combination of SSP with a stack-specific persistence schemes like DirtyBit or Prosper. So how combining a stack-specific scheme with SSSP kind of scheme, how the entire thing will work. So we use computation like SSP is used for both heap and stack, and SSP only used for heap, and either DirtyBit or Prosper is used for stack. So in this figure, we are showing the execution time when these schemes are applied for memory persistence, normalized to execution time when no memory persistence scheme is applied. In this experiment also, we varied the background page merge thread invocation frequency of SSP from 10 microsecond to 1 millisecond. So SSP, when combined with the Prosper very specifically designed for stack, gave advantage, and it reduced the persistent overhead by 2 times on average compared to using SSP with 10 microsecond thread invocation frequency used for the entire memory area. So for all combination, we can see that combining dirty-bit or Prosper with SSP provided benefit as compared to using SSP for the entire memory area. So this table shows the comparison of Prosper with other state-of-the-art memory persistence schemes for properties which are essential for stack persistence. So I summarize my talk with the key takeaways. So Prosper provides sub-page page granularity checkpointing for stack by allowing tracking changes at a lower granularity like 8, 16, 32, 64, any combination of size we can configure Prosper with. And Prosper on an average provide 2.1 times reduction in stack persistent overhead, and maximum it provide 3.6 times. And the paper contains the results for Prosper when different stack usage patterns like stream, sparse pattern of stack usage, and if we vary the checkpoint interval, how that influences the checkpoint size and overhead. So all these results are available in the paper. I request you to refer to the paper for those results. And Prosper complements well with the existing memory persistence schemes to allow persistence for the entire memory region. So Prosper, when combined with SSP, provided 2 times on average and maximum of 2.6 times on average in reducing the memory persistent overhead. And the paper also contains the results on how different that sensitivity to different configuration parameters of the lookup table, like high watermark and low watermark, and how those influence the overhead of a Prosper. And overall, Prosper provide a stack persistence for achieving process persistence. So as we started with, the higher goal for us is to have a process persistence. So after a system crash, we will be able to resume the process from the state when it was before the crash. So I would like to take your questions. Please ask if you have any questions.
Yeah, you can unmute and ask questions directly.
Hi, can you?
Can you briefly go over the security implications for that?
Sorry, I didn't get you.
Uh, Security implications of storing this.
Okay, so yeah, security implication. If I can think about, so this the lookup table is per core. Then so like if you have a hyper-threading kind of scenario, then like mostly the security attacks, because I don't work on security for say, but any shared any shared resources are always prone to attack. That's what I recall from my knowledge from security aspect. So if you think from that angle, then this lookup table that we are maintaining is a shared structure. So maybe then you can mount some attacks on maybe covert channel or side channel attacks you can possible, because that will be shared by the threads which is running on that.
Okay.
So, yeah, other than that, I don't see any security vulnerability in the possible in that.
So I have a small question.
Yes, please.
Uh, is this lookup table exposed to OS? Like I'm thinking if uh, so we eventually when writes are happening, some bits are getting set in this
Yes, correct.
table you are maintaining in hardware. So OS needs to see these bits and based upon them, it has to decide uh, regarding persistence. So how does OS know? Is this table exposed to OS?
Uh, no, the lookup table is a hardware structure. It is not exposed to OS. And to answer your question, so this the lookup table has a high watermark. Like there are different configuration watermarks. So considering a entry reached that watermark and it got evicted, so that in particular bitmap entry will be written into the memory, which is predefined as a bitmap area. So then. So in the current lookup table design, we have 32-bit as a lookup entry. So we have a bitmap area address and 32 bits as a one value. So considering this, some bits are set in the bitmap area. This particular bitmap value will be written into the considering that the watermark scenario is set satisfied, and the particular bitmap store will happen, and that particular memory in the DRAM will be updated with that particular bitmap value which is issued from the core from the lookup table. Then when OS because we are talking about a periodic checkpoint, at the end of the interval, the OS will be reading this bitmap area to know which all bits are set in the bitmap area. So OS comes to know what bits are set by reading this bitmap area, which is a memory allocated in DRAM. So that memory is actually allocated by the or software thread component of Prosper, which is nothing but the OS part of OS. The OS knows what is the base address of that particular bitmap area for a particular execution context. So this bitmap area is per execution context. So we considering a application which is multi-threaded, two threads are there. So there will be one bitmap area for each thread, because as we all know, the stack is per thread. So there will be two bitmap area. Each bitmap area is for the particular thread. And the OS knows for that particular thread what is the bitmap area, and it inspects the bitmap area to know which all bits are set. And based upon that, it copies the modified data from stack in DRAM to NVM copy of that stack. Are you clear, Rohit? So what I
Yes, sir.
what I want to say? Yeah, okay. Thank you.
I have one other question related to this only. So
Yes.
is it possible that some some bits present in your hardware structure, they never get evicted to memory? Like I'm thinking this high watermark is never reached for them.
Yes, so that is possible. A high watermark is never reached. So what we do is that at the end, because we are talking about a periodic checkpoint. So at the end of the checkpoint interval, we force hardware to flush out everything from the lookup table. Like we force everything. Like then every end of the interval, we force all the entry from the lookup table to be flushed out uh, to the memory in the bitmap area. So that the watermark scenario is for normal efficiency, like a new entry has to be created. Then there is no vacancy in the because lookup table we are fixed to 16 entries. So if there is no space in the lookup table entry, then how the eviction will happen. And another scenario for eviction is that the number of bits set in the bitmap particular entry in the lookup table is reached, say 18 bits is being set out of 32, then we will evict. So those all parameters are configurable for the lookup table. Yes, but
Okay.
to answer your question in one line, all the entries in the lookup table will be pushed out at the end of the interval.
Okay, thank you.
Welcome.
Hello.
Yes, please.
It's, hi, Arun. I'm a first year
Hi.
MS student from IITB. Uh,
Yeah.
so I had two questions. Firstly, in the initial part of the talk, how did you identify the active stack region?
Okay. So the active stack region we can identify by the what is the value of the stack pointer, SP pointer. So the base pointer and the stack pointer is maintained in the registers. So we always then looking at what is the stack pointer value and what is the base pointer, we can always derive what is the so at the end of the check, because we are taking decision at the end of the checkpoint. So at the end of the checkpoint happens, then at that point we can read the stack pointer value and check what, then from the stack pointer value till the base pointer value, then that becomes the active stack region. So that is how we identify the what is the stack region which needs to be copied to the to persist to NVM. Are you clear with that answer or yeah?
Yeah, that makes sense. Okay. And secondly, you had 3 configurations for thread invocation interval. Can you highlight what is and why is it important?
Okay. So you're talking about the SSP background thread invocation frequency, right?
Right. Right.
Okay. So yeah. So SSP, as I mentioned, is a shadow page based scheme, which maintains 2 physical pages for a virtual page. So this thread is required because you cannot that whatever the extra buffer pool of pages, what the authors call in their paper, the pool of pages are fixed in size. So consider that some scenario or the condition occurs where the pool is exhausted or there is no free pages available, then you need to merge the addition extra pages into one page so that you can release page back to the pool. So that is the reason there has to be a background thread which comes up in a periodic manner and which goes through this pool of pages and see like what are the duplicate pages and merges it to one page, one physical page, and update the page table entry accordingly, and then release the one extra the freed page into the pool so that other requests can be serviced from that. So now why this thread invocation frequency is important, because this thread is a software thread which has its own overhead. It's a kernel thread is doing this merging of pages. So if you have a higher frequency of invocation, like you invoke the thread more frequently, then you will be merging pages more frequently, but then this thread has to be scheduled in a core. So then the entire system throughput will go down, because now you are scheduling a thread which is for this merging activity, not a applications thread. But now the other extreme, if you reduce the thread invocation, like you invoke thread at a very low frequency, then what will happen is that there will be a shortage of pool pages available. So that is the reason we varied this thread invocation. Thread anyhow has its own overhead, but the frequency of thread also contributes to the overall system throughput. So that is the reason we varied this merge thread invocation frequency. And to add to that point, the original paper of SSP, even though they talk about this background thread, merger thread comes and merges the pages to release the pages, they have not talked about what is a frequency in which the thread is invoked in their experience. So these whatever values that we used in our processor work, these are decided and used by us. Like what I mean to say, there is no value provided in the SSP, the original work. Did I answer your question?
Yes, yes, yeah. Thank you.
Yeah, thank you. Are there any other questions?
Yeah, I guess no one has there to ask questions. Okay, in that case, maybe we'll stop here. So thanks for the talk, and we'll upload it online sometime today or tomorrow.
Okay.
Yeah.
Thanks,
so let me stop the recording first. Yeah, we'll have one more talk sometime in April. Hopefully, we'll get more audience. I guess Holy effect is still on. We have really low turnout today. Anyway, okay.
Yeah,
Thanks.
yeah. Thanks everyone for attending.